Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog.
Welcome to Robbins Library. I'm Andrea Nicolai, the Assistant Director here, and I'm thrilled to invite Science for the Public here tonight. Dr. Thomas Dame, thank you for coming. Yvonne, it's been a pleasure working with you. We're really delighted to have two of the lectures in this wonderful series. So welcome to those of you who have never been here, and welcome back to those of you who have.
Good evening. I'm Yvonne Stapp for Science for the Public, and I welcome you to this science lecture tonight. And tonight it's our great privilege to welcome Thomas Dame, Director of the Radio Telescope Data Center at the Harvard-Smithsonian Center for Astrophysics and Lecturer of Astronomy at Harvard University. Dr. Dame received his PhD from Columbia University and then was a research associate first in the Department of Astronomy at Columbia University and then at NASA Goddard Institute for Space Studies in New York. He joined the staff of the Harvard-Smithsonian Center for Astrophysics as a research astronomer in 1986 and the faculty of Harvard University as a lecturer in 1988. Dr. Dame is a member of the American Astronomical Society, and his many awards include the prestigious Secretary's Research Prize from the Smithsonian Institution in 2009. Although his publications are technical, his discoveries have been described for a more general public, and they're very readable, in magazines such as Scientific American, Discovery, and Science News. I believe I've got some links on our website for you. You'd find the links to the background information about the project itself that he's going to talk about on the Science for the Public webpage for this lecture. Dr. Dame is especially distinguished for his team's radio telescope survey of the entire Milky Way and for the discovery of two unknown spiral arms in our galaxy. This decades-long project as a whole is a huge accomplishment in astrophysics. It was based on two important factors, both of which represented scientific innovations. First was the focus on huge clouds of dense molecular gas in the galaxy, and second was the use of small, nearly identical telescopes in opposite atmospheres. Dr. Dame will explain for us the significance of these factors. We'll learn also about the challenges of this work, what it's revealed, and how it was accomplished. Dr. Dame has given invited lectures all over the United States and the world, so we are really honored to have him with us tonight to bring this great story of his project to the general public. Please welcome Dr. Thomas Dame.
Well, thank you very much for that very nice introduction. I also appreciate each and every one of you for coming out tonight, braving the snow piles and the traffic on Mass Ave. It's very gratifying that you want to come and hear about our research. We have two radio telescopes that are virtually identical, one in each hemisphere, and so we have access to the entire Milky Way, and if we want the entire sky with complete uniformity, right? No troubles with reconciling differences in the equipment and so on. The data collected by these telescopes have produced 24 PhDs within our research group over the years, hundreds of research papers, and as Yvonne mentioned, two of the three significant spiral arm discoveries that have been made over the past 40 years. Okay, so we will move on. This is one of the few bullet bullet slides I will have, I promise. But just to tell you what's coming up, in 50 minutes you can't summarize 35 years of research, but my goals are fairly modest. I'm going to tell you about the telescopes, show you pictures, of course. I'm going to talk about what we observe with these telescopes and why those things are important. How do we do it? So talk a little bit about the instrumentation and the data collection and the data analysis. How do we make sense of what we're observing? What does the data look like? Why is it taking us 35 years to carry out this project and is still going strong? Then I'll talk about the Milky Way Survey that you've seen on this poster. Whoops. And by the way, again, because I'm grateful for you all to come out, I bought copies of this poster if anyone wishes to take one and contemplate it at home. Okay, and finally, I'll discuss some of our recent results on the structure of the Milky Way. Okay, so the telescopes. This telescope was built in 1974 by a fairly small research group at Columbia University. This sits on the top of the Pupine Physics Building, or it did, in the middle of Manhattan, about 100 yards off of Broadway at 116th Street. You can see the Empire State Building in the background. And this is the World Trade Center over here when this picture was taken. It's only, as I said, they're very small. It's only 4 feet across. It looks like it should be sitting on somebody's roof picking up hundreds of cable stations, right? MTV, right? It's not impressive to look at. And also notice that it's not the most ideal location. There's this huge old historic optical telescope which produces an artificial horizon, which we had to have programmed into our software so we knew when we lost our signal in the west. Now, why is it that we can observe in the middle of a city with such a small telescope? And both of those, the answer to both of those things is because we observe at a very high frequency, about 1,000 times higher than FM radio stations. The observing frequency is 115,271 megahertz. 1,000 megahertz is a gigahertz, so it's 115 gigahertz. And the corresponding wavelength, there's always an inverse relationship between frequency and wavelengths. The wavelength is 2.6 millimeters. The key point that I want to emphasize is that the resolving power of any telescope depends on the relative sizes of the wavelength of the radiation you're looking at and the aperture of your collector, whether it's a lens or a mirror, which is essentially what this is for us. This is a mirror, a perfect mirror for the microwaves that are coming in to be observed. So because we're looking at a very short radio wavelength, we can scale down our dish in proportion. And so we obtain, our ability to see details in the sky are as good as those of the big 100-meter telescopes you see in textbooks, because they're generally observing at 100 times longer wavelength. Okay, so we're observing, and that also accounts for why we can observe in the city, because there's virtually no radio interference at these frequencies. At 1,000 times lower frequencies, you have FM, AM, taxi cabs, air traffic controllers, cell phones, but as my own thesis advisor used to like to say, at this frequency, New York City was as quiet as the day Henry Hudson sailed up the river. No interference whatsoever. And that's true also now in Cambridge. So no interference. In 1986, for a lot of reasons, we decided to move from Columbia to the Harvard Center for Astrophysics. Here is the moment, the quite unsettling moment, when our engineer Sam Palmer actually used a jigsaw to cut through all of the cables that were running from our control room on the top floor of the physics building to the roof. And that was definitely the point of no return. And we knew we were going to Cambridge. Here's our current location. On the historic Building D at the Center for Astrophysics. This is not normally how we see the telescope. Normally we observe through this Gore-Tex screen, which is about 99% transparent to the radio waves, but this, for the sake of the photograph. Strangely enough, we still have to contend with a big old optical telescope.
You brought that with you.
We didn't want to bring anything. We didn't want to bring that, but this one is even more historic. I don't want to go off on tangents, but that's a very historical instrument that was built in 1847 during the American Civil War. It was the largest optical telescope in the country. It was the premier instrument of the United States. I've made a lot of important discoveries, but this is another picture. This is how we normally, here's the Gore-Tex screen is down now. I don't even know who took this picture, but I like it very much because it sort of indicates how the old telescope is all shut down, and you have all this light from the city, this light pollution reflecting off the clouds, so it's cloudy, and yet we're still observing away over here. So we can observe through the clouds, we can observe night and day. We have some problems with wet weather, but for the most part, we just chug along day and night, regardless of the clouds. That's just a peek at the Great Refractor, which I like very much. And every third Thursday of the month at the Center for Astrophysics, they have an open house, and you can go and visit that. This is the counterpart, which we built in 1982. It's basically a clone of the first one, right? So once you have all the designs and everything, it's always easy to build another one. So we built another one in 1982, and we brought it down to Cerro Tololo Observatory in Chile in the Andes Mountains. And so this is a comparable picture. That was there from 1982 until 2011. Very recently, they moved it to Santiago to be on the campus of the University of Chile so that they could operate in a vein very much like we do, using it not only for research but also for teaching. And I'll say a little bit more about that in a while. This is I showed you the view from New York City. Here's our view from the Andes Mountains. Quite a different view, but just as spectacular. So what do we observe with this telescope? All right, so if you went outside tonight, if the clouds have held off, and you look to the west at exactly this time, this is almost exactly what you would see, minus the white lines, okay? But a lot of you, if you have any interest in astronomy, any amateur astronomers, will know what constellation this is. Anyone? Orion, thank you. Oh, educated class. Educated. Okay, so there's the Orion Constellation, and the very first spectrum that we took with our northern telescope was on this little object here. This little red patch. Does anyone know what that is? Someone does, I can tell. No? The Orion Nebula. It's the nearest region of massive star formation. You can see it with your eyes. It's a little red patch, and I'll zoom in there for you. Here it is. So this is just a sort of a nice picture of the Orion Nebula. This is a region where massive stars are forming. They're burning their fuel at a copious rate. They're producing a lot of ultraviolet radiation, and they're ionizing the gas, and so the gas is glowing by fluorescence. Okay, so this is called an H2 region. It's a region of ionized hydrogen. And what you can see in front of the H2 regions, and these are new stars that are forming. There are 4 in particular that are called the trapezium that are very famous with amateur astronomers. They love to photograph it. But you can see in front of the H2 region is this dark material, right, which is blocking our view. And that's very dense. That's the very dense gas out of which those stars formed. Okay? Now, the reason we looked toward the Orion Nebula for our first observation is that it had been found that there was actually some molecular gas in that direction. Now, up until about 1970, people thought that molecules were extremely rare in the galaxy and in the universe at large. People thought that the whole subject of chemistry was a very provincial subject, that it stopped a few miles above our heads. Because if you took a typical molecule like CO, carbon monoxide, you just left it in a typical place between the stars, it'll be very quickly dissociated, busted apart by the ultraviolet radiation that pervades the space. Okay, so no one expected that there'd be many molecules. So molecules were, you can find them in these tiny little out-of-the-way places like planets, but they don't amount to much mass. Okay, most of the mass is in stars, and that's ionized, right? So it's not even atoms; it's atoms that have been ripped apart, so the electrons are pulled off, so you have ionized gas, but very little molecules. Anyways, it was not too surprising that there was some molecular gas here. There had been a detection of some emission from carbon monoxide molecules, which happens to be an important molecule in this discussion. And that was not too discussing because this gas is very, very dense, because it's forming stars. It's collapsed gravitationally. And what it's done is it mixed in with the gas is a little bit of dust. And that's crucial to this whole experiment and the whole situation, because that dust, what the dust does is block out the ultraviolet radiation. So if you were inside one of these dense clouds and you looked out, you wouldn't see any stars. It would be literally dark. So no ultraviolet radiation is able to get in, and that allows these fragile molecules to form. But what was not anticipated was how extensive the molecular gas was. So let me go back to this picture, okay? And what I'm going to show you now is one of our first maps of a so-called giant molecular cloud. So this is what you see with your eyes, and this is what we see with our radio telescope, okay? And it's quite amazing, because if you think about it, if you went out and you could see this thing, it would be as big as a thundercloud, you know, hanging over your house, right? It's like that big in the sky. And no one had any clue about these objects, you know, 40 years ago, okay? And this is the classic giant molecular cloud. And if you go back to, if I can go back to the previous slide, you can see that this is, of course, false color, just like a weather map telling you how hard it's raining, right? But you can see that the strongest emission that we detected is exactly where the Orion Nebula is, right? But I remember doing this map, and we were all astonished at how the cloud just kept going and going and going. I remember the graduate student who was mapping this cloud, he got a piece of graph paper, and the piece of graph paper was about that big, right? And he made little boxes, and he wrote the number in each box and how strong the signal was, and they said, whoa, it went off the graph paper. So he got another piece of graph paper, and he taped it on, and he kept going, and he got another piece of graph paper. And by the time the season was over, the graph paper was as big as the floor area here, literally. And it was just getting more and more unruly, and it just kept going and going. It was totally unexpected. And so what we're seeing here is one of these giant molecular clouds. And so now let me show you maybe a picture that you might be familiar with. This is one of the famous pictures from the Hubble Space Telescope. And this is a little piece of a molecular cloud, right? And so this is the dark, dense molecular gas with dust mixed in, and of course the dust is crucial for keeping it alive, keeping the molecules from being dissociated. You see young stars forming. This is a very bright star, which is literally, you know, melting away these pillars through its ultraviolet radiation. So it's just like an icicle that's melting. So these things will eventually just disappear, and you can see these little globules where the gas is even denser, and there's probably a star forming in here, for example, which will eventually emerge. This is my favorite. This is another Hubble telescope picture of a little piece of a molecular cloud. What I love about this is that it literally looks like a cocoon. It really gives you a three-dimensional sense. This is all molecular gas, and you see that inside this little cavity are these young stars which have lit up the inside of the cavity, and they're busting out, you know, from the molecular gas. So the molecular clouds are the star factories of the galaxy. Virtually all star formation takes place in these clouds. Okay, so you can actually see molecular clouds with your eyes, not from Arlington, not from Cambridge, but if you go to Maine, or if you go someplace really dark, you can see the molecular clouds as a band running along the Milky Way, right? So a lot of you have probably seen the Milky Way. You have to go someplace far away. But all of this dark material is the molecular gas, okay? Now, years ago, 100 years ago, these regions were thought to be actual holes in the star density, right? These are places where there were fewer stars. But I can prove to you, using our data, that they're not holes. Okay, so this is just another panorama of the Milky Way. It's just been laid out in a rectangular way. The galactic center in the middle, and then the anti-center at either end. So this wraps all the way around the sky. I'm going to pull out a little piece of it, and then what I'm going to do is overlay again one of our maps from our telescope, and I'm going to have it blink. Okay? And you can see how all of those dark regions, which had previously been thought to be actual holes in the gas density, holes in the star density, are actually glowing in this emission that we observe, right? And it's a beautiful correlation, right? Every place where it's dark, that's where the molecules form, and we're detecting the emission from those dense molecular clouds. Okay? It would be lovely, I would give my right arm to take a picture of the Milky Way this way, right? But we're in the plane of the Milky Way, so it's very, very hard to figure out what's happening, right? That's the whole challenge of this work. But here's another galaxy which is probably something like the Milky Way. Okay, this is called the Whirlpool Galaxy, or M51, and I show it to you because you can see that you can see these things I was talking about now on a grand galactic scale. You can see all these dense lanes, which are giant molecular clouds, and peppered along the arms of these red patches, which are exactly like the Orion Nebula, places where stars are forming. So the young stars that are forming from the molecular clouds are tracing out the spiral structure of the galaxy. And that's one of my main interests, is to use the molecular clouds to map out their distribution and therefore determine the spiral structure of the Milky Way. This is a map, just again a CO map, one of these radio maps. This one happens to be not made by our telescopes, but by a bigger telescope. But you can see how beautifully the emission in the radio traces out these spiral arms. And so we assume that the same thing is happening in the Milky Way. Okay? Okay, last bullet slide. But the molecular clouds are so important, I want to make sure all the key facts are gotten across, right? So they're the main sites of star formation. That is why most astronomers are so interested in molecular clouds, because they study star formation. It's a very, very complicated process. 10 times more people study star formation than galactic structure. Half of the gas in the galaxy we now know is in this chemical form. Okay, so half the gas in the galaxy is chemical. There's a whole new field of study called astrochemistry, looking at all the amazing and rare chemical reactions that take place in these clouds, because the conditions are so different than what you can produce on Earth. So we have all of these, some very common molecules, but some very exotic ones as well, discovered in these dense cores of molecular clouds. They are well-defined traces of galactic structure. The key point here is that unlike in the optical, where you can't see very far because of that veil of dust, with radio telescopes you can peer right through the dust and look all the way across the galaxy and detect these molecular clouds, which is a few minutes of observations. These clouds, the universe is mainly hydrogen and helium. Helium is a noble gas, so it doesn't form molecules. So when you do form molecules, it's almost purely molecular hydrogen, right? 99.999. Unfortunately, molecular hydrogen, because of the structure of that molecule, it's symmetric, it's said to have no dipole moment, and so it doesn't emit in the radio regime the way other molecules do. Unfortunately, there's another molecule after hydrogen and helium. The next two abundant elements are carbon and oxygen, because they're the common ashes of nuclear burning in stars. So the stars burn hydrogen and helium into carbon and oxygen and nitrogen. So these are common as well. They're way down, but they're common, and they form a good stable molecule. And so what we do is we observe the emission from carbon monoxide, and we use it as a stain or a tracer of where the molecular gas is. So it's a very indirect thing, but fortunately this ratio of CO to H2 seems to be pretty constant. And so it seems to be a quite faithful tracer of where the molecules are. Okay, so how do we observe? So now I'm getting into like what really are we looking at, and how do we detect things? Okay, so here we are inside a molecular cloud. Here's that ratio, 1 CO molecule to 100,000 H2 molecules. So you have all this H2 around, and then you have 1 CO molecule, and occasionally, well, more than occasionally, a hydrogen molecule will come along and get the CO molecule spinning. Now, because at very small scales, because of quantum mechanics, the molecule can't just slow down any way it wants to. It has to continue to rotate at exactly the same rate until at some point, in the case of CO, it's usually months, like maybe 6 months will go by, and then spontaneously and unpredictably, it'll slow down. It'll make a jump. It'll make what we call a transition from a higher rotational state, a higher energy state, to a lower energy state. Right? So it suddenly slows down, and so now where does the energy go? It goes off as a photon of radiation at 115 gigahertz. Okay, so every molecule has a different frequency that it emits, and that allows us to identify all these different molecules because they all have their own fingerprint. They all have their own set of frequencies that they emit. Then what happens? Well, this molecular cloud is halfway across the galaxy, and so it takes a journey of some tens of thousands of years to come across the galaxy, and then finally, some night when my student is sitting there sleeping, in comes the 150 gigahertz. But don't worry, the computer recorded the result anyways. Okay. So, yes. So you would think that all we needed to do, the way we run a radio telescope, this is just the antenna, right? It's called a Cassegrain configuration. It focuses the radiation down into that hole where we have a detector. And so you can imagine we could just hook a radio up to the detector, and then we would tune it to 115 gigahertz, which is the frequency of the CO molecule, and we would just record how much power we get in each direction. But it's not that simple, and it's not that simple because of something called the Doppler effect, which most of you have probably heard about and you've all experienced. If you're standing along the side of a highway and a car goes by, it has a higher frequency when it's coming towards you and a lower frequency when it's going away. And loosely speaking, what happens is that when an object is moving like a car, the sound waves get bunched up in front of it, so you hear a higher frequency, or a higher frequency, which means a shorter wavelength because the waves are getting bunched up in front of it. And the opposite happens when the car's going away. The waves gets drawn out. And a similar thing happens with electromagnetic radiation, like radio waves and light. So that's the red shift, or the Doppler shift. So as I say, that's our bread and butter, because most of our interesting information on the structure of the galaxy comes through the Doppler effect. The fact that we can measure the Doppler shift, because we know exactly what frequency the carbon monoxide molecule is supposed to emit, and then we can measure what frequency we actually detect. And then there's a very simple relationship between the frequency shift and the velocity of the cloud. Okay? So here we are. And so if the cloud is just sitting out there and not moving with respect to us, we will detect it at 115 gigahertz. If it's moving away from us, we'll detect it at a lower frequency, 114. It's coming towards us, 116. Okay? So you can imagine what we need to do is hook up our telescope to, or go to Radio Shack and get a gigahertz band Sony radio. Okay, you can't do that, but someday. But what you can do is just like hook it up, and then you can scan across this thing, right? And so mainly what you would hear is static, because as I said, there's not much interference. So you're not going to hear taxi cabs and radio stations. You're just going to hear static. Shh. But as you scan across, when you get to 114 gigahertz, you'll hear a pure tone. And then it'll go away again as you keep going, right? So just if you tune the radio very precisely, you'll hear a tone, you'll hear a high level of signal at 114 gigahertz, and that will tell you that there's a molecular cloud out there which is moving away from us at a certain speed, which you can calculate from the difference between the rest frequency, which is this, and that frequency. And these are all just, exaggerated. The shifts are actually not that large. They're much, much smaller, but you get the idea. Okay, and also what's nice is that you can have them all. You can have many clouds along the line of sight. So if you aim your telescope through the plane of the Milky Way, you may see 5, 6, 7, 8 different clouds along the line of sight. And unlike in the optical, where you can only see the first cloud, which is sitting right in front of your nose, in our case, we can see all of the clouds along the line of sight, and we can measure the velocity for each one. This cloud is transparent to this cloud because they're at different frequencies. So this radiation just goes right through that cloud, and this radiation goes right through both of those clouds because they're all at different frequencies. Okay? So if you could sort of have your assistant listening to the radio, we don't really listen. Our engineer likes to say that a radio telescope is a telescope you don't look through attached to a radio you don't listen to. Which doesn't excite the kids very much, but you can imagine in some way just measuring the power or the noise coming in, the signal strength as a function of frequency as you turn the dial, and you'll get this, right? You'll get a beep at 16 and a beep at 15, and that's a spectrum. That's our basic unit of data. Okay, and so of course we do that. Now what I just described of just turning the dial, that's a perfectly good way to do it. The reason that's not a great way to do it is because you're only listening, accumulating signal from this cloud for a very short time, and then you keep going. Whereas these signals are so weak that you really need to look at them for a fairly long time in order to accumulate enough signal to actually hear it above the static. Okay, so that's not the ideal way to do it. The ideal way to do it is to have lots of radios. So this is quite a busy figure, but this is the whole experiment in a nutshell, as I say. Right. So the way we do it is, here's our telescope. Right. This is a version, sort of a schematic of the galaxy. Here we are out at the sun, and we're observing through the plane of the galaxy. And what we do is we take the signal, we feed it into a whole bank of radios, 512 radios in our case, and each radio is tuned to a slightly different frequency, right? And so they're all listening at the same time, and the computer, 20 times a second, just reads out the amount of power which is being detected at each frequency, and it just plots it up just the way I did on the previous slide. And that's a CO spectrum, right? So in this case, what we see is if we have clouds along the line of sight through the galaxy, we don't have a pointer, do we? Because this is losing. You know what I can use is the one of those posters, because it keeps like conking out. Oh, do you have a pointer?
It's not a pointer.
Oh, I see. Okay, I'll use this. All right. So you can see that as we look through a typical line of sight through the galaxy, clouds have different velocities, and so they will all show up at different frequencies, but you can convert this axis from frequency to velocity. Okay? And so that's the basic unit of a spectrum, and we do that, typically those observations take a few minutes. The important point let me see if it goes. Yeah. So the important point to make here is that all of our studies only work because the galaxy rotates differentially. It rotates faster in the inner regions than in the outer regions. If the galaxy rotated like a phonograph record or like a merry-go-round, then all of these lines would all show up at 0, right? Because if you're on a merry-go-round, all the other horses are not moving with respect to you. They're going in a circle, but they're not moving with respect to you. And the Doppler shift only tells you about relative motions of the source and the detector. So if you're on a merry-go-round, you get no Doppler shifts from any horses, and that would be the same thing. Fortunately, spiral galaxies, including our own, rotates in a differential manner like water going down a drain, loosely speaking, so the inner parts spin around fast, so that if you see a cloud which is moving at 100 kilometers per second, it means it's deep in the inner galaxy. So that's a crucial point in how we sort out the structure of the galaxy. We use velocity as a surrogate for distance. Okay? This is another view, a rear view of our telescope in Cambridge. Let's see what we got here. So here's the Gore-Tex screen. That's an optical telescope. You might imagine it's kind of hard to point a telescope like this. You're observing in the daytime. You're observing through a Gore-Tex screen. You're actually in the control room in the other room. So occasionally you have to actually have a sanity check. So what we do is this optical scope is aligned with the radio axis, and we open the Gore-Tex, and we just come in and we have it point at lots of stars all over the sky. And we record the errors on each star, and then we do a least squares fit, right? And we optimize the pointing. Okay, it's very nice system, works perfectly fine. So the signals that we're detecting, I talked about hearing a loud beep when we get on these molecular clouds, but in fact these signals are extraordinarily weak. Someone once calculated that all of the energy collected by all of the radio telescopes since radio astronomy was invented in the 1940s and 50s, all of that energy together is less than the energy of a single snowflake hitting the ground. So we're looking at extraordinarily weak signals. In the units that we use, typical lines, typical intensities of these signals are 1 degree Kelvin, and the amount of noise or static that we're contending with is typically 600, 700, 800 Kelvin. Okay, so the noise is hundreds and hundreds of times stronger than the signal. So how do you ever get around that? You use statistics. You use the fact that noise is a random process, so that no matter how weak the signal is, if you wait long enough, the noise is effectively going to average to 0, whereas the actual signal will eventually peak out like coming out of the grass as it's cut. Okay. So you can always detect a signal, you just have to wait long enough. So in order to reduce the amount of static, one of the main sources of static is the receiver itself, okay, the electronics. So one of the ways of reducing the static is to keep the receiver very cold. We keep the receiver almost as cold as humanly possible. It's kept at 4 degrees Kelvin, which is minus 452 degrees Fahrenheit. So 4 degrees above absolute zero, using liquid helium. Okay, so this is a helium dewar, which contains the liquid helium, which has to be refilled every 12 hours when we're observing, every 24 hours when we're not observing. Also, in our case, the liquid helium is even more important because at the heart of the receiver is something called the Josephson junction, which requires the use of superconductors. And of course, the metals would not become superconducting until they get below about 10 K. Okay, so we have to keep this thing super cold. I pointed out the whiteboard just to make the point that this telescope is also used in quite a few Harvard undergraduate courses. It's a wonderful pedagogical tool. Students learn how to use the telescope. It's very hands-on. There's no operators. They just get in there and tinker with it. They learn how it works. They learn what the data means, and then they go and they're given a whole night on the telescope, and they have to design an experiment to measure how fast the galaxy rotates, what the distribution of molecules is, and so on. So it's a great resource for teaching at the university. If I zoom in on sort of one of the plates here, you see that virtually everything in the whole dome is labeled, right? So there's two purposes for that. One is for the sake of the students, so they can actually see how all the signals are processed and amplified and isolated and so on. And also when a student calls me at 3 o'clock in the morning and I tell him to go tune the gun oscillator by 10 degrees, he knows how to do that, right? So everything is labeled. This is the procedure we go through about every 12 hours to put liquid helium into the telescope. This is my postdoc Tulin, and she's dipping these dewars of liquid helium to measure the level. And then we have this lift which goes up to the level of the dewar, and then we use helium gas, which is here, to force the liquid helium through the tube. Okay. Last Saturday, one of my students made a really heroic effort to do the fill. The fill was due within minutes, and she got to the telescope, and there was a drift 5 feet high, and she couldn't get out to the roof, and she tried to go out the window of the control room, and then she came back and she got a shovel and shoveled with one hand outside the door, and then she got to the dome door, and then there was a huge ice block there. And so anyways, you always have to do these fills, New Year's Eve and Christmas Day, and because you always have to keep it at 4 degrees Kelvin. Otherwise you threaten. And so here's Tulin pouring liquid nitrogen, which is also used in an outer can, and here's an actual helium fill in progress. This is the control room. I'll just zoom in on the control monitor. There's a couple of fun things there. There's a little gauge that tells us how much helium is left, right, full and empty. It tells us how much more time we have before we have to do a helium fill. Here's one of those spectra that I was talking about. This is the actual data. This is all you get to see at the radio telescope. You don't see any pretty images like I've been showing you. You just see spectra, right? And it's only much later when you have thousands of spectra that you put them all together and make these maps. Okay, but this is a spectrum with radio velocity along here. This is the strength of the signal, and these are all these different peaks at different clouds along the line of sight. The dewar temperature is always displayed. When it starts to go up, the computer sends email to everybody who knows how to do a helium fill. But if it's Sunday morning at 3 a.m., that doesn't help very much. Well, for the students, it usually does work. But anyways, so here's the rest frequency of the line, for example, 115.271.201. So you enter commands here. So that's sort of what, this is where you're sitting most of the time. This is just a little fun fact. This is our original computer. So the older people in the room will appreciate this. This is a Data General mini computer, which is a really hot machine back in 1973. It cost us $10,000. I had 16-bit words, 64 kilobytes of core memory. I don't know if anyone remembers kilobytes, but the entire telescope was run almost as well as it is now, and the data was written on these punch tapes, paper punch tapes. And it's not, nowadays you don't see bits very often, but these are actual bits, right? So it's like 16 bits across, so that's the actual data, and you can read the individual bits. And it was lots of fun to work with, because you had it was a 16-bit machine, and you had these 16 switches, and you could toggle in addresses, and you could deposit, you could change individual memory locations, and then just start the program running again. So you're basically doing programming with those switches, which people don't do anymore. But it was quite a fun machine. Okay, why does it take so long? Okay, let's go back to this picture that I showed you before. This optical photograph probably took somebody 2 seconds. If they want to get a nice deep image and see the nebula. This radio map took us 16 months, observing 5 hours a day. 5 hours is how long Orion is up in the sky, high enough to be observed with a radio telescope. Okay, so a big difference in time. Why? Well, because someone used a 6 megapixel camera, right? That means that camera has 6 million pixels. And each pixel samples a different spot on the sky, and then so you click the shutter and you get a picture, right? The problem we have is that we have only 1 pixel. We have 1 pixel. And not only that, but as I mentioned, the signal is very weak. Okay, so we have to integrate to beat down, we have to integrate to beat down the noise. So typically 3 to 4 minutes. Sometimes you're looking at another galaxy, you might have to integrate for an hour per point. but typically a few minutes. Okay, so that's why it takes so long, is we have this, you have a single pixel. This is the pixel up here. So the detector is very sensitive. You know, we've got all this trouble of cooling it down to liquid helium temperature, but there's only one of them. Okay, so when we observe, we only get the average emission from a tiny spot on the sky called the beam, which is this little dot here, which you may be able to see, right? And it's 9 arc-minutes across. So that's our resolution. That determines the resolution of our observation, just like the size of the pixels on your TV screen determine how much detail you can see of the football players. Okay. So again, just to drive that point home again, if we decide we want to map a little region of the sky where we think there may be molecular gas because there's a lack of stars, the way we have to do it is we have to look at, one point at a time, bump, 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 and build up these images. When we're done, you know, each position gives us a spectrum, and then ultimately we use that data to make a map. Okay, so that's the process. Now you would say, well, you know, gosh, all that trouble and all you get is this map, right? Well, you know, that's not true. As I said, at every single position we get a spectrum, right? So essentially we have a third dimension to the data, which is not displayed on that map. Even this poster here, which shows this image of the entire Milky Way, that's just the tip of the iceberg in terms of the amount of information that's in the survey, because at every single point in that map we have a spectrum, right? So in fact, our maps are three-dimensional. Okay, so this is meant to. So this is just the same. This is just a piece of the Orion map, right? And now I'm going to just turn it into a grayscale and then let it spin, right? So there's a lot more information in these maps. So what you're seeing is the velocity. So the third dimension is velocity, right? So it would be nice if the third dimension were actually distance, but it's not. So you're not looking at a real object in 3 dimensions rotating. It's 2 dimensions on the sky, and then the third dimension is velocity. But there's an awful lot of information there. You can see rings and expansion and jets and things and so on in that map. But that's why the data is such a challenge to analyze. So let me go back and just say a little bit more now about the Milky Way. And first of all, you know, again, this is an optical image, and you can see that if you look at an external spiral galaxy like NGC 891, edge on, which happens to be edge on to our line of sight, it looks rather like this panorama, right? Because we are indeed right in the plane of the Milky Way, and so we see a very similar thing. These are all these molecular clouds in NGC 891. So here's a highly schematic view of the Milky Way. These are just a schematic image of the spiral arms. The sun is out here. This is from edge on. The sun is here. We have these globular clusters which were formed early and tend to scatter around the center of the galaxy. The point that I made before is that we can't see optically much further than a region like that, right? So most of the galaxy was excluded from study until the 1950s and 60s when radio astronomy got going. The first person who got his arms around the entire Milky Way was Harlow Shapley, who was the director of the Harvard College Observatory for more than 30 years, one of my heroes. And the way he got a handle on the size of the Milky Way is that he looked at the globular clusters. And so he studied these globular clusters, so basically he looked above and below the dust. And he saw these objects, and what he discovered is, hey, the objects aren't they aren't uniformly around the sun. They're mainly over in that direction, in the direction of Sagittarius, and they seem to form a sort of a spherical distribution about a point about 30,000 light years that way. So he is sometimes called the Copernicus of the Milky Way, because what he did, just like Copernicus showed that the Earth wasn't the center of the solar system, he showed that the sun was not the center of the Milky Way. So here's a headline from the 1921 Boston Sunday Advertiser indicating that the universe is 1,000 times bigger, Harvard astronomer discovers, right? So he realized that and of course they call it the universe because at that time the Milky Way was thought to be the entire universe. Okay, they had seen these external spiral nebula, but they called them nebula because they thought they were very close, and they didn't realize that they were actually galaxies just like our own. Okay, just as a totally irrelevant sidelight. Harlow Shapley's office, when he was the director, was right here, was directly below our telescope, and I'm sure he wouldn't like our rumbling dome. So it's sort of good that it worked out the way it did. But anyways, in the 1950s, people worked really hard studying the distribution of young stars that have just formed in this region and they discovered that, hey, they seem to line up in 3 lanes. Okay? And so that was the first evidence that we were in a spiral galaxy. So you can see the lane here, a lane here, and a lane here. It's not all that convincing, but he did get a standing ovation at the American Astronomical Society meeting as being the first direct evidence that indicated that we were in a spiral galaxy. The real progress came with with radio astronomy. You look across the galaxy in a direction like that, and to make a point I made before, if the galaxy was just rotating as a phonograph record, that's what you would see. You would just see one big strong line at 0, and you would have no information whatsoever on the structure of the Milky Way. And I would be an economist or something. I don't know. But this is all, that's why our bread and butter is the fact that the galaxy rotates differentially, and so what you really see is that. Okay? So the emission is all spread out in velocity thanks to the differential rotation of the galaxy. So if you look on that side, of course, everything's moving away from us, right? Because the galaxy is spinning like this. So if you look on this side, everything's going away, so all the velocities are positive. If you look on the other side, they're all negative. So that's what you see, right? And so again, as I pointed out, you can relate velocity to distance. So if you see something at a low velocity, it has to be fairly close to the sun, so it may be here. As you look at a higher velocity peak, that has to be further out, maybe at B. And if you see a really high velocity feature, that has to be deep in the inner galaxy. And see, so you can really work out there. You can actually work out directly. There's a relationship between distance and velocity. There's some difficulties with that, but that's the basic idea. This is again just a map, sort of like what I showed you before. You can see Orion in the lower right. So this is now a map of the entire Milky Way. Now we didn't set out to do this originally. We didn't, it's not all uniform. It was done by many people for many different reasons, many different graduate students, basically every different color there. So that shows how the Milky Way was actually observed by all these different surveys. Basically, you can see probably 10 to 12 different PhD theses in there, right? And each person got a little chunk of the sky, chunk of the Milky Way to study and write a thesis about. So that's how it's divided up. And it turned out that we ended up with about 34 different surveys. Eventually we said, hey, we almost have it all, so let's just fill in the gaps and publish it, right? So this is the certainly our most important publication in 2001, where we published all of our surveys from the past 20 years in this Astrophysical Journal research paper, and never before and never again, I believe, will the APJ allow a 5-page foldout. I've never seen anything like it. They didn't blink an eye, and they said, sure, no problem. And so we have this 5-page foldout, which is basically that image up there, a little bit more detailed. Okay, let's think about this data again. A point I made is that at every point on this map, you have a spectrum, right? So what you really have is a 3-dimensional data set. Okay, so if you can imagine looking down on the data set from above, that's what you would see. Okay, now even astronomers, when you're at meetings and you introduce one of these weird diagrams called the longitude, this angle here is called longitude, this is velocity, so this is a longitude velocity diagram. And when you introduce those at an astronomy meeting, you hear groans. Because it's really hard to relate to, right? Because this is not distance, unfortunately. So it's really, but what this is really is just a highly distorted map of the distribution of molecular gas in the galaxy. You just have to know how to interpret it. And so our group is particularly adept at interpreting and identifying features in these so-called longitude velocity diagrams. And so that diagram is what's on the bottom of that poster. Okay, so these two maps are just two perspectives on what is really a 3-dimensional data set. So the data set is very much, almost essentially is the same as a CAT scan of a human brain, right? So we have the same, we have the same problems, like with a doctor trying to identify a tumor in a brain after a CAT scan or an MRI. He has this 3-dimensional data set, and he takes cuts through it, and he cuts it different ways. And we do exactly the same thing. In fact, there's currently a project going on at Harvard called the Astronomical Medicine Project. Now, there's been billions of dollars spent on writing software to interpret MRIs. Okay, the budget for that is probably 10 times the entire budget of astronomy in the United States. So we can leverage all of that work to analyze our data because it's exactly the same problem. Okay, so here's those two maps. Okay, the sky map and the velocity map. So what do you see in that map? Well, there's a lot of stuff you see. It's hard to come to grips with. Again, so this axis is longitude, just angle along the Milky Way in both cases. But in this case, it's velocity on this axis as opposed to just angle up and down. So what can you see? Well, one thing you see is just galactic rotation. Okay, so you look on one side of the galactic center, all the emission is positive, which means it's moving away from us. On the other side, it's negative, which means it's coming towards us. If you go back to this image, remember, it's only relative motions that cause Doppler shifts. So if you look directly toward the galactic center and everything's moving in circular orbits, you should see no Doppler shifts at all. So all of those lines should overlap at 0. Right? I sort of mentioned that before. So because everything's moving perpendicular to our line of sight. So what we should see when we look toward the galactic center is just 0 velocity emission. What we actually see is just the opposite. Okay? We see huge expansion motions and very fast rotation, but mainly expansion. You see emission from minus 300 kilometers a second to almost plus 300 kilometers per second. So that's actual expansion of gas from the galactic center due to God knows what. Due to an outburst phase in the Milky Way in the past, possibly due to infall on a black hole. There's lots of theories for what causes that outflow. But again, it's not what you'd expect. It was quite unexpected. But it's very dramatic. You can also see spiral arms. This is a very obvious one. This is called the Perseus arm, right? So it's a linear feature. And I've overlaid some other spiral arms, the outer arm and the local arm. And there's a lot of arms in here too, but it takes a lot of work to sort of pull them out. Okay, and that's sort of a lot of things we do. Here's the poster, which shows those two maps. As I said, you're welcome to have copies. Okay, so this is an artist's conception of the Milky Way. Now, we can't take a picture like that, but an artist, guided by many, many research studies and experts in the field, has come up with this image of the Milky Way. And it shows some interesting features of the Milky Way that have just been discovered or proposed in the past 10 to 20 years. Okay, and one of the most important ones is that the Milky Way is a spiral galaxy, but it's also a special kind of spiral. It's called a barred spiral. And that simply means that the central concentration of stars is not in a spherical distribution, but it's rather in an oblong distribution. Okay? And it's just many theoretical studies have shown that if you start off with a spherical distribution of stars, there's a great tendency for it to go into this more stable oblong configuration. So about half of spiral galaxies are so-called barred spirals. I'll show you an extreme example of a barred spiral galaxy. This is NGC 1300. This is the granddaddy of all barred spirals, right? So you have this huge bar in the middle and these fantastic symmetric arms coming off either end. Okay? So that made us wonder if we're in a barred. So bars tend to drive quite pretty symmetric spiral structure. Not always, but it was an interesting find, a very interesting find, an important find. And so what the evidence is accumulating now that we may have something like that happening in the Milky Way. We have this arm called the Scutum Centaurus arm, which comes off one end of the bar, and we have the Perseus arm coming off the other end of the bar. And then there's some minor arms in between. But it has been suggested, it's far from proven, but it's been suggested that these two arms dominate the spiral structure of the galaxy. So that's one of the issues that we've been deeply involved in. But this map is, again, an artist's rendition based on the best knowledge we have. But in order to fill in the details, it required a fair amount of interpolation, extrapolation, and in some cases just wishful thinking. Okay? So what do we really know about the distribution of gas in the galaxy? Okay? Well, let me strip off all the labels, go to a grayscale representation. And what I'm going to show you is the arms that most people agreed upon in late 2007, early 2008. If you sat down, most people would agree that these arms existed. They could see them in the longitude velocity diagrams like the one I showed you. But if you, especially if you take away the galaxy artist drawing, you can see something rather disturbing about what we know about the galaxy. Basically, we only see half the galaxy, right? Okay, so all this discussion about the Milky Way having a beautiful symmetry, where is it? Okay, how can you have symmetry if you only have half of it? It's the other side, but so we don't see much over there, right? It's very hard. It gets very, it's very difficult. Things, the inverse square law affects us like it does all astronomers. In any case, what we have done, what we have contributed to this picture in the last few years are two spiral arms. One of them called the far 3 kiloparsec arm. This was quite a startling discovery because what we found was that this arm was a virtual mirror image of this arm. Okay, so one of the most respected people in the field noted that this was the first direct evidence that the galaxy really had a twofold symmetry. Okay, and it was quite unexpected. This arm had been known since the 1950s. It was very obvious in the data. Most galaxies are pretty messy. Okay, I've showed you some really pretty galaxies so far, but this is more typical, right? So you have spiral arms in there, but where are the main arms? How many arms are there? It's quite a mess. Okay, and it's a bit depressing to go through a catalog of galaxies because most of them look like that. Okay, so this was very exciting that hey, at last we got something that suggests symmetry in the galaxy. Okay. How much time? I need to know how much time because I can skip over 5 more minutes. Okay. Okay. So let me just say. So yeah, this is the quote. Some of the first evidence that the galaxy has a twofold symmetry. Let me just very quickly show. I can't get into details on how we found this thing. It was quite an exciting time. But if you zoom in on the central part of the longitude velocity diagram, so this is just zooming in between plus or minus 12 degrees, this turned it to a grayscale, which happens to be a lot better for just seeing linear features. You can see this structure here, which hits you in the face. Okay, that's the near the 3 kiloparsec arm. I learned about it on my mother's knee in the 1950s. Okay, and you can see that there it is. And remember, when you look directly toward the galactic center, you should not see any radial motions. But in fact, in this case, when you look right toward the galactic center, the arm has a velocity of minus 53 kilometers per second. So it's absolutely unique in the galaxy in that sense. Most of the other arms are coming through here. There's really, really strong lane here. All the other arms in the galaxy are behaving themselves, and they're going to 0 velocity at 0 longitude. Not that one. Okay? So it was a real puzzle. What was causing that? Well, there was two prevailing theories. There was an explosion, and this was an arm that was exploded out from the center. But if that's the case, where's the backside? Right? Where's the backside of the arm? You look over here, you don't see it. Okay? And so that's the expanding 3 kiloparsec arm discovered in 1957. What I'm going to do is jump to another version of this LV diagram, which we created. I was in the process of preparing a talk for a meeting on spiral structure, and I just wanted to show people the known arms as clearly as possible so that people are at least all on the same page in terms of believing the arms that that most people believed in. So I just wanted to show them all. But in the process, I made this figure, and then this. Now I don't know if you can see that, but it's at first it's not all that impressive. It sort of looked like a set of muddy tire tracks running through the middle of the LV diagram. Okay, here's this galactic center, right? So you have these 2 lanes, and I'll tell you, when I first saw that, I've seen a lot of interesting things in my career. Most of the time, when you see something interesting, the more you look at it, the less interesting it becomes. Okay, it sort of dissolves like cigarette ash in your fingers. It's just, it's very heartbreaking. Okay, in this case, it was the opposite. So I saw this thing, and the funny thing is I went home at night, and I have a good relationship with my wife, but I didn't even mention it to her because maybe I just want to jinx myself, but also I know what usually happens. I'm going to go in the next day, and I'm going to calculate how big it is and how what the mass is, and it's not going to match up at all. Okay? It turns out that the more I looked at it, the remarkable thing is that these things, when you calculate their properties, they're virtual twins. Okay, the one in the far side arm is much weaker and harder to see because it's 3 times further away. Okay, so that's to be expected. Okay, if you look at the velocity, it's almost the same velocity, within 3 kilometers a second in the other direction. Okay, Just moving on. Since then, I've gone to Australia, got much better data on this thing, so now it's somewhat more believable now, right? You can see this thing. No doubt, nobody has raised serious doubts about it. These are all of the properties of the two arms that we worked out. I don't have to go through them all. But basically, they're symmetric twins, okay? The other thing that we've added back in 2011 is a large structure way out here, the most distant arm that's ever been seen, because the sun is here, and we spotted this thing way out here. Okay, first in the atomic gas, and then with CO observations. And it's kind of remarkable that the most distant molecular clouds in the galaxy have been detected by the smallest radio telescope able to observe molecular clouds. Okay, so one of the projects we're working on right now is mapping this thing very thoroughly in CO emission. The significance of that arm is that we believe, through modeling and analysis, that it is the extension of the Scutum-Centaurus arm. So there's this theory that the Scutum-Centaurus arm is one of the two major arms of the galaxy, but this is all we knew about it. That doesn't look very major, right? So now we think, well, wow, if that's really the end of this, it's going almost 360 degrees around the galaxy, okay? So that supports this idea that Scutum-Centaurus is really a major arm of the galaxy. One of the things we can do now, it's a very well-defined test. If you go back to our image, we found this piece here, the outer Scutum-Centaurus arm, and again, addressing this issue of symmetry, one direct test that we can perform, and we can get a yes or no answer to, is if there's a symmetry in the galaxy, then the outer Scutum-Centaurus arm that we discovered should look like the Perseus arm at the opposite position. And the nice thing is that the Perseus arm is very close to the sun. Okay? So we have lots of good data on the Perseus arm, so we just have to work really hard. These observations take about 45 minutes per point because it's so far away. But if we map this thing thoroughly and compare the properties with the Perseus arm, we'll have a yes-no answer on whether there's any symmetry there, as we saw between the near and the far-3 KPC arms. So those are the type of issues we're dealing with. I went through the catalog. This is one of the galaxies that I think probably looks like the Milky Way, M109. So there's a lot of work ahead, surprisingly. But I think I definitely will stop there and just ask for any questions.